Okay, hello Risab, welcome to my channel. So let's dive into this problem. So I think the fundamental topic that you need to understand is what it means for an object to roll without slipping and how it arises. So if we just look at our system initially, you have your wheel. Let me change this column real quick. So you have your wheel. It's dropped on the ground. And say this is axis rotation. It has some angular velocity, call that omega naught. It has no translational velocity. So now when we're dealing with rolling without slipping problems, the point that you are most concerned about is not the center of mass, but is this point of contact with the ground. So because of this rotation about the axis, the velocity of the point that is touching the ground, and since this is a rigid body, there's only one point touching the ground. That's not how it works in real life. There's no such thing as rigid bodies in real life. Material science doesn't come that far, but if we have this wheel, hypothetically, theoretically, we should just have one point touching the ground. And the velocity of that point, due to this rotation, will be, of course, omega r, omega naught times r. So what is this cause? So if you have, this point is in contact with the surface. This point also has a velocity relative to this surface, and that velocity is going this way. So if we go back to thinking about how friction works fundamentally, friction is a contact force, so we have something in contact here. And friction arises when you have a relative velocity between two surfaces. So this point right here has a relative velocity with this surface, which is the ground. So since friction always tries to oppose motion, and in this case the velocity is this way, the frictional force exerted at that point will be this way. Now what does that do? That creates a frictional torque that opposes the existing angular velocity. So now angular velocity will start to go this way, and it accelerates the center of mass forward. So if you try to imagine like a bowling ball or something, if you spin a ball and you drop it on the ground, it starts going forward, right? Or like a billiard ball or something. This is essentially what's happening. Another way to think about this is when you have something that is, spinning this way, it's sort of like hitting the ground, right? Like if it's spinning like this, you keep hitting the ground. So by Newton's third law, there's going to be a frictional force that hits back at that point, and that causes this frictional force here. Now, we want to find how much time it takes for the wheel to slip, how much time the wheel slips for. So it'll stop slipping when you start rolling without slipping. So what will that look like? Well, we have our wheel again. And it has a different angular velocity because this torque is decreasing this initial angular velocity. But we know that if something is rolling, it's still going to have an angular velocity in the clockwise direction. So we'll call that omega f. But now it's also going to have a velocity forward. The center of mass will have a velocity forward. And we say that a wheel is rolling without slipping, or an object is rolling without slipping, when the center of mass is equal to omega r. Now this equation is all fine and dandy, but why is that the case? Well, if we look at this point of contact again. So let's look at the velocity of this point of contact. Again, you have a velocity due to this rotation, the tangential velocity due to the rotation, which is going to be omega f times r. But now you also have a velocity due to the center of mass, right? Because if this point is moving through space, it has a tangential velocity due to this rotation. But if it's moving this way in space, there's also this contributing to this velocity here. And by saying that the velocity of the center of mass is equal to omega r, we're saying that these two quantities are equal. So what that does is make the velocity of this point right here relative to the ground 0. And as we discussed before, friction arises from a relative velocity between two surfaces. If the velocity of this point is 0 now, there is no longer any relative velocity between this point and the ground. Therefore, there is no more friction. When an object is rolling without friction, I mean, when an object is rolling without slipping, there is no more friction acting on that object. So with that in mind, let us start our calculations. So we can first begin by considering just the center of mass. And we said that there's a frictional force acting this way, which is just equal to mu mg. So then the acceleration of the center of mass is equal to mu g. Now let's consider the rotation about this axis. So I alpha, since it's a solid disk or whatever it is, then the torque acting on it is friction. We'll say that a counterclockwise torque produces a positive. Counterclockwise is positive for torque. So then we start plugging in some numbers. Friction is still just mu mg r. So then some stuff starts canceling out. Very nice. And we get alpha is equal to 2 mu g all over r. Now, we want to achieve this condition from here. So we want omega naught equal to, so we'll just start with, so we want this velocity of the center of mass starting from 0. And now, obviously, since this frictional force is acting forward, it will help us attain this velocity of center of mass. And since it's also producing a counterclockwise torque, it will reduce this angular velocity until the point that the velocity of the center of mass is equal to the angular velocity times the radius, at which point there will be no more friction, so there's no more torque, and everything stays the same. So we can start just by writing, we want velocity of the center of mass equal to omega final times r, and that'll just be given by the acceleration of the center of mass times time, just some basic kinematics. Then we have the final angular velocity, which will be given by alpha t, which is 2 mu g over r times t. However, we also have this initial angular velocity. And since we're saying that clockwise is negative, counterclockwise is positive, we can say minus omega naught. So now you have your system of equations. You have two unknowns, omega final and t. So you can start doing some cool and epic algebra. So r is equal to mu gt. Let me just scroll the clock. 2 mu gt minus omega naught r is equal to mu gt. And you get that t is equal to, sorry, run it back. The velocity of the center of mass is not going to equal omega fr. It is going to equal negative omega fr. Because as we said, this point has to be stationary, right? So the velocity of the center of mass is going this way, and omega fr is going the other way. So when we write omega fr, we're talking about the magnitude of this angular velocity. So it's going to be, since this angular velocity is going to be going this way, we want the velocity of the center of mass to be opposite. Sorry, this tangential velocity, right? Because omega fr is this tangential velocity. And we want the velocity of the center of mass to be opposite that, so that's why we have that negative there. So then you just do some substitutioning, and you get 2 mu gt over r minus omega naught mu gt. Now if we continue with our algebraic manipulation, gt, and you get that between t r t over g, and this will come out to be 1 second. Yeah.